Imagine a single coordinate in a two-dimensional void. We tether a second point to it with a fixed length and allow it to sweep a continuous path through space. This path represents a locus, a set of coordinates that satisfy a rigorous mathematical condition. For a circle, that condition is equidistance. Every coordinate on this trail must exist at the exact same distance from the central anchor. The familiar closed curve of the perimeter is the geometric expression of that single rule. This rigid distance constraint functions as the generative engine, ensuring that every rotation results in an identical figure. By establishing this law of equal radii, we create a system where specific internal theorems become inevitable and provable. These hidden laws govern how multiple points interact, how internal segments are divided, and how angles are measured. Understanding the circle requires looking past the boundary line to the invisible mechanics generated by the center point. If we place 3 random points on a plane, provided they aren't in a straight line, only one unique circle can connect all of them. We start with 2 points, A and B. We drop a perpendicular line bisecting the segment between them. This bisector is the locus of points equidistant from A and B. Placing a center anywhere here guarantees intersecting both coordinates. Introducing a third point, C, requires a second constraint. We draw a new perpendicular bisector between points A and C. Because these 2 bisector lines are not parallel, they intersect at a single specific coordinate, which we label O. This intersection is unique. 2 non-parallel lines on a plane can only meet at one point. Because point O lies on both bisectors, it is mathematically equidistant from A, B, and C at the same time. This exact coordinate is known as the circumcenter. Using O as the center and the distance to A as the radius, we can draw the circumcircle. It is the only circle that can touch all 3 points. This rule holds regardless of the point's positions. Shifting the coordinates moves the circumcenter outside the triangle for obtuse angles, or onto the hypotenuse for right angles. The linear distances between these points strictly dictate the radius of the circle that encompasses them. We can also use these radii to analyze the interior mechanics of the circle. Any line segment connecting 2 points on the circle is a chord. Suppose we have 2 separate chords, AB and DE, of equal length. We need to determine if they create identical angles at the center point, C. We connect the endpoints of each chord back to the center, forming 2 triangles. Our known data is that both chords are equal and all the segments connecting to the center are radii. By definition, every radius in this circle is exactly the same length. This allows us to apply the side-side-side congruence postulate. Triangles ACB and DCE share 3 pairs of equal sides, making them identical. Since the triangles are identical, the angles they subtend at the center must be exactly equal. This logic is reversible. If we start with 2 equal central angles, the side-angle-side postulate proves the resulting chords must be equal. The circle functions as a symmetry operator, maintaining consistent internal dimensions regardless of where the chords are placed. We can examine this symmetry further by looking at a single chord, AB, and its midpoint, M. We draw a line segment connecting the center C directly to that midpoint. To find the angle of this intersection, we rely on the triangles formed by the radii. By drawing radii CA and CB, we create 2 internal triangles that share the line CM. Again, side-side-side congruence applies. The radii are equal, the chord segments AM and BM are equal, and they share the middle segment CM. Because these triangles are congruent, the 2 angles sitting on the chord at point M must be identical. A straight line is 180 degrees. For these 2 adjacent angles to be equal, they must both be exactly 90 degrees. This proves that any line from the center to a chord's midpoint is naturally perpendicular to that chord. Combining these proofs reveals a complex interlocking geometric system. The curved boundary of the circle acts as a visual shell, but the structural integrity is defined by the internal segments we have derived. If we remove the perimeter, we are left with a perfectly symmetrical web of radii and congruent triangles. Every relationship in the system originated from the single rule of equidistance. This rule generated a unique center point from 3 random coordinates in space. It enforced the unbreakable symmetry between internal angles and chords. The circle operates as an engine of invariant radii, maintaining absolute consistency across all points on the plane. True mathematical insight comes from mapping the invisible, unbreakable laws that generate these figures.